Everyone, welcome to Codec channel. Today we are diving deep into one of the most fundamental yet often overlooked mechanisms in iOS development, that is the run loop. If you have ever wondered what happens behind the scenes when your app launches, how your UI updates, or why your animations work so smoothly, this video would answer all those questions out for you. So run loops are the invisible engines that keep your iOS app running smoothly. They manage everything from user interactions to UI updates. Yet many developers have only a surface level understanding of how they work. So by the end of this video, you'll have a thorough understanding of run loops, which will help you build more efficient and responsive applications. So with that, let's dive in. Before we even get to that familiar view did load function, which you could see out over in this called stack, uh, many complex series of events have already occurred out, as you can even see in this stack trace, like all of these. And amongst them is also these UI application main and start and main that you can see. So this entire thing is what we call an app launch sequence. So when your app launches, the operating system initializes your app's environment, sets up the main thread, and calls the main function that you see. And this might sound basic, but understanding this process is pretty crucial for comprehending how exactly the iOS application works. So the main function has one primary responsibility, that is to call the UI application main that you see, and this one. So what do we need UI application main for? Well, I would say it has many responsibilities. Like it creates the shared UI application instance and your application delegate. It even sets up necessary components to run your UI application, including scenes and delegate setup. Most importantly, for our discussion today, it starts the main event loop by calling runloop.run. So it's also responsible for like running the run loop, I would say. The run loop is what keeps your application alive and responsive. Without it, your app would execute its code and then just immediately terminate. This is how exactly the UI application dot main looks like, this entire part. So main has one responsibility of calling UI application main, and UI application main is further responsible for creating the run loop via run loop dot run, which we've discussed about. So now let's jump into what run loop is. So what exactly is a run loop? I would just go off by simply saying it's an infinite cycle of events happening inside the app. So consider it as an event processing loop that we use to schedule work and coordinate incoming events. It's just implementation of that infinite cycle of events happening in your app. So in the world of software architecture, run loop is an implementation of what we see as an event loop. The primary purpose of run loop is to keep your thread busy when there is work and to put it to sleep when there isn't. This efficiency is crucial for mobile application where battery life is a key consideration. Let's consider this diagram of what we mentioned before, an event loop. And this diagram illustrates the fundamental concept of run loop as an infinite cycle of events. The diagram shows a circular arrow representing the continuous nature of run loop. This is crucial to understand. Unlike a typical function that executes and run loop keep running throughout the lifetime of your app, processing events as they arrive. Like these tasks that you see out over here, this part, It just keeps on coming. The tasks keep on coming. So this infinite cycle is designed to wait for a task, process the events that come in, execute any callbacks if there are any, and return to the waiting state to await the new task to show up. So this is the cycle that keeps our app responsive rather than executing once and terminating. So this was the event loop, and run loop is an implementation of an event loop pattern. And this diagram that we see, this is how exactly a run loop looks like in iOS. So there are multiple different sources like an input source, a timer source, and these input sources they just deliver async events out, and this might be in message from the other threads or maybe from a different application. Whereas timer sources are also async events, but they're recurring or maybe occurring at a scheduled time, I would say. So the best way to understand run loop is to think of them as waiters in restaurants. So they're constantly checking if their orders could be like termed as an events for our case. So if there are any orders, they'll process it one by one. If there aren't any orders, they'll just not go off running aimlessly, which would waste energy, but rather go off into an awaiting state. That's what run loop does as well. And yeah, so diving a bit deeper into technical implementation, run loops in iOS are built on the core foundation, that is CF run loop. And when we look at the core foundation code, we can see several key run loop events that are just kind of defined out by the CF run loop itself. So the run loop ensures all the main thread code that you happen to write executes one of these functions. By one of these functions means the ones that I've mentioned out over here. So these function names might look intimidating, but they reveal something very important. The run loop ensures that all the main thread work is executed through these functions. Each have a specific purpose, like handling different types of events happening around in your application. Okay, so let me go off explaining you what each of these function exactly does. This CF run loop is servicing the main dispatch queue. It handles tasks submitted to the main dispatch queue. CF run loop is calling out a block, basically executes the blocks of codes. CF run loop is calling out to a timer callback function, basically timer events. That's what it processes. Now you will see there are like two kind of sources, source zero and source one. CF run loop is calling out to a source zero and a source one perform function. So handle source zero events, basically it's more of towards apps internal function calls, whereas source one is more of towards kernel events, which we will be talking out very soon. In fact, the very next topic. The next is CF run loop is calling out an observer callback function, the last one, and it processes the observer callbacks as the name suggests. This diagram that you see out basically emphasizes the run loop funnels all the main thread work through the dedicated function, ensuring orderly processing of different event types. A run loop source is essentially a way to indicate that some event has happened at some other point in your application or maybe in a different process. And the run loop should handle this by calling the related callback. So sources again, two types, source zero and source one that we discussed earlier about. So source zero is more about inner app communication, whereas source one is more of towards inter-process communication. It's also termed as IPC. So let's understand source zero a bit more. Source zero is basically managed out by your application. When source zero is ready to fire, some other part of your application, maybe a code on a different thread, calls CF run loop source signal function to tell the run loop that it must wake up for the source to be handled. A good example of source zero is UI kits touch events. Basically, when we put a breakpoint on UI buttons tab selector, we happen to see a source zero event happening. Like if I see this is like view controllers button tabbed, and if we check out over here, it just says calling out to a source zero perform function. So this kind of proves that like UI kits touch event is a more of like source zero, and it should be because it happens to be managed by the application itself. Okay, so coming on to source one is a bit different because it is managed out by kernel. These sources are automatically signaled by the kernel when a message arrived at the source's MAC port. For those who don't understand kernel, so kernel is a fundamental part of an operating system that kind of acts as a bridge between computers hardware and software. Whereas Mac port is something that just allows processes to send and receive messages securely. So each process interacts with kernel via these Mac ports. So it's an abstract way for processes to communicate without knowing of the physical address or any other such info. For example, like if an application needs to communicate with some other app or maybe to the system, it does so via these MAC ports and this source one event that we're talking about. Uh, A real world example of source one could be when our app needs to communicate out with system, such as receiving notifications about hardware like orientation changes, basically setting your changing the orientation into a horizontal or vertical, or maybe battery status updates and such. Okay, so after just discussing about what run loops are, like let's jump in to understand the very next topic, that is core animation. And we gotta understand how core animation integrates with the run loop because it's very critical to understand how UI updates itself. So under the hood of UI kit lies a lower level framework called this core animation that you see out. Yeah. So UI kit delegates a significant portion of UI related tasks such as animations, layout, and rendering to this core animation block that we see. So every UI that you happen to create is associated to a CA layer. So when a UI view is created, it automatically creates a CA layer under the hood and set itself as the layers delegate. So many properties and method of UI view that you happen to even use are just proxied properties of the underlying CA layer. Okay, so as you can even see out in the diagram, the UI view, and then there's a CA layer, and then there's the CA layer delegate, which the UI view assigns to itself, and properties such as these uh, frame, background, and bounds, whatever we set out in the UI view, it's just basically delegating out to the CA layer. Uh, for it to be performed. Okay, so there are three kind of layers, like one being model layer tree, the second one being presentation layer tree, and the third one being the render tree. So these are the three different layer trees that core animation manages out. It just doesn't manages CA layer, but these are the other trees that it goes off managing. So what exactly is a model layer tree? It is what your app interacts with the most directly. When you change a property of a layer, A model layer tree is something that we are working out with. Next comes the presentation layer tree. It contains the in-flight values of running animations. So it just happens to reflect the very current values appearing that appears on the screen. So we shouldn't go off modifying the objects in the presentation layer tree that I am talking about, because it just happens to be very real time. And to be honest, like the presentation layer is not an original layer, but it's more of like a ghost layer. It's just an approximated state of what we call a render tree. And a render tree is something that performs the actual animation, and it's kind of set as private to the core animation, and it just happens to be the closest to the actual screen state. And it's very important to understand that the presentation layer is not original, but sort of a shadow. The UI changes are not applied and updated on screen every time that we kind of change something out, but core animation kind of sort of groups it all together into what we call a CA transaction. So suppose I'm going off changing frame bounds or anything of that sort. Individually, it wouldn't go off applying those changes off, and more or less those changes are going to be applied to the model layer tree that we're talking about. So, what exactly is a CA transaction? A CA transaction is a mechanism for grouping multiple layer tree operations into just an atomic update to render the tree. So, this happens to be very crucial for performance, and the reason being, if we just go off applying one by one, it obviously is very inefficient. And what CA transaction does is simply just kind of groups all the changes and then goes off applying this group onto the screen state. When and where is this CA transaction happening? So how does core animation interact with the run loop? This is where the things get interesting. This diagram, the core animation kind of is observing the run loop iteration via this CF run loop before waiting event. And this arrow kind of symbolizes that it just happens after every run loop iteration. So to sum it up, after every run loop iteration, core animation is observing the run loop before waiting event. And based on that, if the layer has changed, it go off implicitly adding a CA transaction. Uh, CA transaction again goes off implementing whatever the changes have been made. If the layer tree has changed, only then. If not, it just simply returns itself. And so basically, core animation observes the event, and when this event fires at the end of the run loop iteration, if any changes has happened to the model layer tree, like maybe the bounds have changed or the animations have been added, the core animation groups these changes into a single transaction and commits it to be applied to the render tree. An implicit transaction is created only if there are changes in the model tree. So if we go ahead and put a breakpoint in the layout subviews, this is what we are bound to see. We see that there is the CF run loop is calling for an observer callback function. So basically, it's just kind of just waiting, observing for the event. And while the core animation sends the implicit transaction on every run loop iteration, the transactions could also be handled out in an explicit way. So by explicit way, I just mean you can yourself just say the transaction CA transaction dot begin or CA transaction dot commit, and in between them we can go off handling any sort of changes in the model tree that we just kind of happen to require. And yeah, so basically the CA transaction, it just consists of four phases. the layout phase, the display phase, the prepare phase, and the commit phase. So what we'll try to understand in the initial is uh, the layout and the display phases. So coming on to the layout and the display phase, because that's what happens to update my UI. Basically, this is what we term as the UI update cycle. So let's look into how a UI update cycle looks like. So in this diagram that we see, there's user interaction that happens to enter in an event queue. So every user interaction, there's a queue, and these user interactions just get appended to the queue. And these user interactions are picked through these event queue by the application object. So the application then dispatches these events to the event handlers, which consists of whatever the developer code has been written down, and this in turns returns itself back to the main run loop or the application object that we are talking about. This triggers the very start of the update cycle. The interface is updated, the layout and the redraw views, and then it just updates the app interface and returns the control back to the main run loop. And this main run loop is going to indeed take another event then out of the event queue and go off with handling its handler, executing whatever developer specific code. So developer specific code is the place where you've written down all the state changes, and then once these states have been changed, it just starts off the update cycle, which consists of layout and redrawing of views, and the same thing just happens to go around. So what exactly is an update cycle? So update cycle is the point at which control returns to the main run loop after app finishes running all event handling code. So typically we request a change in a view while processing the event handlers, and the system marks the view for a redraw. So at the very next update cycle, the system executes all the changes on these views. And for a lag-free user experience, iOS typically run at a 60 FPS, that's 60 frames per second, meaning this entire refresh cycle happens to occur in 1/60th of a second. That's around 16.7 millisecond, which is a very short window of time. So although the system processes events very quickly, there's a slight delay that happens to be there between event handling and the actual view update. Uh, And any code that depends on the view's latest content or layout may run into an issues because of this lag of the state information during this interval. So, this is how exactly an update cycle looks like. So basically, the main run loop points out to the update cycle, which happens to point back to the main run loop itself. Okay. So there are multiple things that happen, like the layout, the redrawing of the views. There's also one constraint changes, which we'll discuss further. So the very first thing that comes up is the layout, and a view's layout refers to the size and position on the screen. So the frame defines where the view exists in the super view's coordinate, whereas the bound is in its own coordinates. Uh, so the UI view provides us with the method that kind of notifies out when the view's layout has changed. And those methods are like the very first is layout subviews. And layout subviews is basically it just happens to handle the repositioning and resizing of a view and its subviews. It gives the current view and every subview a location and a size, and it just happens to be a very expensive call because it acts on all subviews of a view and calls the methods recursively. We should not call it explicitly. Instead, we should call the method that triggers it out. So when a layout subview complete, a call to viewed layout subviews is triggered in the view controller that owns the view. So many of us might have seen this viewed layout subviews and viewed layout, viewed appear, and so on. So this is important since viewed layout subviews is the only method that is reliable uh, for calling after a view's layout is updated. So we should put any logic that depends on layout and sizing in viewed layout subviews and not in viewed load and viewed appear. Next come the set needs layout. So this is the very least expensive way to trigger layout subviews. It runs and immediately returns without updating views. Instead, the view will update in the very next update cycle. The subview layouts are also updated in this case, and the delay between calling it and the actual layout is small. So we should generally prefer using set needs layout. Next comes in layout if needed. So when we call layout if needed, the system immediately updates the layout of the view and subviews if there are any pending changes. So for those pending changes to happen to be there, we can mark a view as needing a layout using the set needs layout that we earlier discussed. So it's used when we need layout to change immediately. It's commonly used in an animation block to ensure all the pending layouts changes are applied before animating. And yeah, this covers up the layout part. Next comes the display. So display encompasses the properties of view like color, text, images, core graphic drawing, and it also has some key methods, just as layout had. The layout subview, set needs layout, layout if needed. It too has a draw and set needs display. So a draw has a purpose to draw shapes, text, or images. Like layout subviews, we should not call it directly. Instead, call methods that trigger draw at different points in the run loop, like we did in this set needs layout. So set needs display, it marks a view for redrawing, just like set needs layout marks a view for updating its layout. With this method, we basically are telling the system that view's content has been updated and it needs to be redrawn in the next cycle. So during that next update cycle, if the view has been marked as needing a display, the system calls the draw method to update its content. So basically, like if it needs a display, the system would call in the draw method, and draw method, which in turn would just go off drawing the custom content. So if our view requires custom drawing, we can override this draw. And when a property that affects the custom drawing changes, we can trigger set needs display. Next, just as a display and layout comes in constraints. So constraints are basically used when we want to update the constraints of the system. So what happens is the system recalculates and set all the required constraints on the view. So just as the layout and display, it too has its own methods. That is update constraints, set needs update constraints if needed, invalidate intrinsic content size. So first is update constraints. So this method can be used to dynamically change the constraints in a view that uses auto layout. We should just implement constraints that are subject to change in update constraints. Also, we should not implement it directly. Just we shouldn't implement draw directly. We shouldn't implement layout subviews directly. Neither should we directly call in update constraints. So next comes in the set needs update constraints. So calling it again guarantees a constraint update in the next update cycle. So it triggers update constraints by marking that one of the views constraints have been updated. Next comes in the update constraints if needed. So basically, it checks the constraint update flag and determines if constraint needs updating. If so, it triggers the update constraints immediately and doesn't wait till the end of the run loop. The next comes in invalidate intrinsic content size. What invalidate intrinsic content size does is it would set the flag indicating the content, indicating the view's intrinsic content size as stale and needs to be recalculated in the next layout pass. So this covers up the constraints, display, and layout. So yeah, this is a generic table for like just depicting out the layout change, the display, the constraint, the same layout subviews, the same as draw in terms of display and update constraints in terms of constraints. Then comes set needs layout. So it's pretty much the same thing as we had discussed earlier. Okay. So there's an init with frame, which would indeed call all these three set needs display, set needs update, constraint, set needs display, which would check other constraints required. If so, let's update the constraints. If not, go ahead, check. Do we need to update the layout? If no, skip to needs display. If yes, go on with the layout subviews. And needs display again checks if yes, uh, draw whatever shape or anything that you require. If no, it handles uh, back to the event loop, which in turn calls it back. Now that we have discussed the two parts that are layout display, there are two more parts to a CA transaction, uh, namely prepare and commit. So what a prepare phase does is it does additional core animation work like image decoding and image conversion. Whereas the commit phase, it just packs up the layer tree and sends the transaction to the render server to apply it to the render tree. So basically what's happening around is every time we kind of make changes out to the tree, we send out the updates via layout, display, and so the commit phase, what it does, it packs it up into a layer tree, and further, this layer tree is just sent out to a render server, and render server is just kind of sends the request via IPC to the metal. Metal in turns happens to draw these pixel bitmap via everything that's been given out in the instruction in the render tree, and that pixel bitmap is kind of shown onto the screen. So this illustration that's kind of drawn out over here, this is exactly how a bitmap image looks like. So at the end of every run loop, this happens to redraw itself according to whatever layout, constraint, or display changes that have been requested out. Okay, so there's also one thing that we gotta keep in mind, that is when managing this layout if needed and set needs layout, we just need to ensure that the constraint doesn't recursively updates itself. So what happens is it would cause a circular dependency with the auto layout. So sometimes forcing layouts can cause circular dependencies in the auto layout. For example, layout if needed triggers a constrained update, which depends further on another update. So this might lead to an infinite loop, or it might cause a crash. Okay, so this is the layout phase, and this is the display phase that we earlier talked about. And as you might see in this diagram, that the traversal just happens to be there from leaf to the super view, that is bottom up. And again, like layout sub layers and layout sub views. So basically this is a view, and the layout sub views again calls in the update constraints, which further goes off with needs update constraints. And so this is the constraint pass, this is the layout pass, and this is the display pass. Okay, let's cover this diagram out. So the very first thing that happens is we launch the app, as we had discussed. The it further just happens to call out UI application main. UI application main has one important responsibility, that is to call runloop.run. Runloop.run further, we discussed core animation, and it just kind of looks out for that event before waiting event that we talked about. The Yeah, so it keeps on looking out for that, and once it gets it, it just goes off with looking out for is if there is any implicit CA transaction commit that is there, and if so, it goes off with the layout and display phases, in which it just happens to find out whatever the changes have been there, which in turn updates the UI and prepare for the commit phases. And we happen to even discuss that once that commit phase has happened, it further passes to the render server, where render server is responsible for passing it further down to metal, and metal creates such bitmap for the screen to render out again and again via passing it out to GPU, then GPU passing the same pixel bitmap to the screen's display, which in turn displays out the changes. And again, once this thing happened, this again goes off into calling the run loop, and this entire process just happens out to be there, like happening every 1/60th of a second. So what's happening around over here is again, there's this launch. It sets up the main thread, which in turn calls main calls the UI main application. The UI application starts in with the run loop iteration. Run loop iteration basically has this event called CF run loop before waiting, and it just keeps on looking out for this event. And uh, what happens is once this event happens to be there, the core animation is notified. So it's the core animation which is kind of observing this event out. So once this event happens, and what happens is it just gives a call back to the core animation to start updating the update cycle. And as update cycle we had discussed, it further has this layout constraint as well as draw that it keeps on checking out for this layout. Sorry, yeah, this layout, display, prepare, commit, the four parts of CA transaction that we talked about. So basically what happens is once it gets a callback, it checks if the layer tree has been modified. If no, it just simply returns out. If yes, it goes off creating a CA transaction, and CA transaction is nothing but a pack of all the changes. And once that CA transaction happens out, it goes off setting layout, display, then it prepares whatever that you've created out, and then commits. Once it has been committed out, the via IPC. So one important thing to note down is via IPC, it sends out to the render server, and the render server again just deserializes it into a render tree, and further sends the command to the metal, and metals further sends it to GPU. GPU further creates a bitmap, a pixel bitmap, and which in turn is shown in the screen. So another important thing to look out over here is that all these layout, display, set if needs layout, set if needs display, and all those set if needed constraints, all those we are calling off from our application code, which in turn notices if there's any changes in the model layer tree or in the presentation layer. And if there are any, we go off explicitly calling those CA transaction one thing to note down over here is CA loop.run. This is what UI application dot main calls in. And if there are no such events, what it does is the run loop just simply sleeps and wait for sources or main block to handle and give it events. And once it receive events, it start processing out. And the process involves source zero, source one, observers, timers, main queue, as we have already discussed out. So this sums up very much like how basically UI is handled out at the app level. Basically, understanding these concepts is going to help you with debugging the UI issues more efficiently, optimizing the app's performance, and creating much smoother animations and building more responsive user interfaces. So one good thing to remember out is while the run loop handles a lot of things automatically, knowing when to use method like set needs layout, layout if needed, or set needs display would actually give you a more precise control about apps UI updates. So that's it for today's deep dive into run loops. If you found this video helpful, please hit the like button and subscribe to Codec channel for more in-depth iOS development content. You could drop your questions in the comment and I'll do my best to answer them out. Thanks for watching and happy coding.